Everyone see that? Okay. So we were talking about space debris and what it is, etc. And so here we have the Earth. And you can see that there's a lot of stuff out there. 90% of all this stuff is non-functional. Its use is over with. There are two main debris fields. One is this ring here, and these are the geostationary orbit, Earth orbit. So these satellites are always above that particular part of the Earth, and they move around with the Earth. And the other is this swarm here of objects in low Earth orbit. So the geostationary orbit is at about 38,000 kilometers above Earth, and this swarm goes to about 2,000 kilometers. Now, the International Space Station operates at 400 kilometers, and the Hubble at 600 kilometers. So they're not necessarily being bothered by these main objects. And this debris can include things like non-functional spacecraft, abandoned launch vehicles, mission-related debris and fragmentation, spent derelict satellites or derelict satellites, spent rocket stages, as well as from fragments from all those things, their disintegration and erosion and collisions. As of October 2019, the US Space Surveillance Network reported that there are nearly 20,000 artificial objects in orbit around Earth, including just over 2,000 operational satellites and 34,000 pieces larger than 10 centimeters. And these are very easily tracked. However, there are also more than 128 million pieces of debris smaller than 1 centimeter, and about 1 million pieces between the 1 and the 10 centimeter size. And there's a new radar station going up in New Zealand, and it's going to be tracking about 250,000 of these objects between 2 and 10 centimeters. And already, seeing as we're littering stuff up there, several spacecraft, both manned and unmanned, have actually been damaged or destroyed by space debris. This debris is tracked very carefully. The space station sometimes has to maneuver around a piece, or 2 other of the satellites might have to sort of adjust their orbits or their to not hit each other. And it's becoming more and more crowded up there, as you can guess. I think I already mentioned that Elon Musk wants to put up about 15,000 satellites in orbit, and they'll be in this type of orbit, so close to the Earth, about 500 kilometers up. So what can you do about all this junk? Well, I'm pretty sure that the astronauts will not be gathering the debris. And I thought this one was interesting, that somebody has talked about having actual vacuum in space. Well, space is already a pretty good vacuum, better than any vacuum we can do on Earth. So this kind of a concept of just sucking up the pieces is just not going to happen. The 2 things you need to do to all this junk, you can either deorbit it, so it burns up in the atmosphere, or boost it to what's called a graveyard orbit, which is just above that geosynchronous orbit of that ring around the Earth. Different ways to do this could be light sails. So this is a very, very thin, like a mylar type material that uses photon pressure from the sun to move, so we can readjust the orbits and either deorbit or send it to a higher orbit. Nets are thought to possibly work, and the European Space Agency is working on a mission right now where it'll go out. So here's the little CubeSat. It'll go out and throw a net around the object, which will then slow it down so it can deorbit. Lasers, either from Earth or up in space, can be used, again, just light pressure to move orbits slightly, to deorbit them. You could actually send up little CubeSats, which are equipped with small thrusters that will then attach to an object and move its orbit. And there's also sort of like a space Roomba being thought about. It's a kind of a double-armed satellite, would rendezvous with an object, use one arm to grab hold of it, and the second to apply like a solid propellant rocket, which would deorbit. The mission that's being worked on right now with this is very modest. It only plans to remove 35 of the objects over a 7-year time span, and it would just target those that are the biggest threats. So 35 out of the millions is a good start, I guess you could say. And the International Telecommunication Union, which you have to go through if you're going to launch any satellites, now requires proof that a satellite can be moved out of its orbital slot at the end of its lifetime, although this also has many problems. They haven't worked out all the fine details of that, that's for sure. Any questions about space debris?
Was there a particular time when a whole bunch of debris or things got put up there? Like, is there, like, I imagine a whole bunch would be from early expeditions into space.
Absolutely, yeah, absolutely. You know, 1950s, nothing. And then once Sputnik was up in 61, I think it was, then it's that same logarithmic growth. You get a few happening and then higher and higher. And of course, when they were first putting stuff up there, they weren't concerned about it. There was a lot of empty space. There was a lot of, you know, no worry about things hitting each other. It's just that it's gotten so crowded and is a potential. These things, you know, like I say, 1 to 10 centimeters, they're pretty small, but they're moving at about 28,000 kilometers an hour. So the size times the velocity gives a really big impact. And the window on the shuttle has been hit and cracked, and you know, it's a pretty hostile environment outside those spacecrafts, especially for the manned objects, that you really need to. Now we're only thinking about the mitigation of what we can do to clean up this area. It's a very big problem, though, as you can see.
So these are just these are ideas that that people have put forth for
Yes.
getting rid of the debris. Is anybody working on any of these? Is anybody? It's all just ideas. It's all just.
Yeah. And I don't know how far in the future. Hopefully soon. I mean, these like the European Space Agency doing this NetCap. I think they hope to deploy that fairly soon. But yeah, nothing has been really started yet. Proof of concept, they do have some, the Planetary Society do have some sails up there, that light sails that they're using to see about propulsion. So we can get them up there and deploy them. It would just, how do you stick them to something and then deorbit it? And you really don't have to worry about the deorbit, about anybody getting hit. I think there's only been one case where space debris has actually hit somebody. It was somebody's shoulder or something like that, minor damage. If you look at the Earth, most of it's going to deorbit into the Pacific Ocean. Anything that doesn't burn up there and land there will be in Siberia or China, because that's the largest landmass. So the deorbiting will mostly have everything burn up if anything does happen to come through.
Here with an important announcement. Support for farmers and
Hold
agriculture
on.
as they cope with the COVID-19 pandemic and the associated economic crisis. I'm here with Minister of Agriculture, Deb Dreeshen, and of course, Chief Medical Officer for Health, Dr. Dina Henshaw, who will follow this important economic announcement with today's daily COVID-19 update. We know that farmers have been seriously affected by the global economic crisis.
Okay, back to this. Sorry about that. I've been following the COVID crisis quite closely. Okay, so we can move on to life in the universe. And if we look at the different conditions on Earth, we can see a wide variety of systems. The Earth has temperature ranges from -90 to +60 degrees Celsius, illumination levels from areas that are completely dark to continual sunshine, pressures that range from 30 kilopascals, which is at the top of Mount Everest, 100 at sea level, to 100,000 kilopascals at the bottom of the ocean, and humidity levels from arid to completely saturated. And we find life everywhere here. So life can adapt to all these different types of conditions. So we could expect life on other exoplanets if we find these kind of conditions. The only place on Earth that does not have life, this was just found recently, is in Ethiopia's geothermal field. This water is very acidic, very salty, and very hot, up to about 113 Celsius. So there might actually be a life limit, at least in respect to these types of conditions. Conditions on Earth that we think are favorable to life. We have a long-lived star. So life on Earth started very quickly, but it took about, so we've heard, about 3.5 billion years to go from single cell to complex life. Very massive stars have a very short lifespan in the order of millions to tens of millions of years. They also emit very high levels of ultraviolet, which can easily break bonds of the molecules of life. Very low mass stars, the red dwarfs, can live for hundreds of billions of years, so that's good for life, but they do have peculiar properties that may not make them very suitable for evolving life. Their low temperatures mean that their habitable zones, or that Goldilocks zones, the area, the distance out from the star where liquid water can exist, are so close to the planets that the planets are so close to the star that the planets would be tidally locked. So this means one side is always facing the star, so it would be hot. The other side is always facing out into space. It would be very cold. So really only leaves a band of habitability at the edge of the day and night line. Unless if there is a significant or a substantial atmosphere that could carry heat around to partly of the dark side, so mitigate that a little bit, but for the most part, tidally locked planets around M dwarfs would not be a good thing. And M dwarfs also have very violent outbursts, just the way they're constructed as compared to larger stars. And so that may quickly extinguish any life if it ever gets started. Earth also has an almost circular orbit around our sun, which allows stable conditions to exist for a prolonged time. The Earth is in the habitable zone of our star, again, which means liquid water can exist on the surface. And Earth is massive enough that it has a molten outer core, which spins, which produces a magnetic field. And these magnetic fields, they can deflect solar storms and cosmic rays. Most cosmic rays are made out of helium nuclei moving at velocities of about 0.4 to 0.99 c, or the speed of light. And again, the faster you go, the more damage you can do. A large Earth, also a massive Earth, also allows it to keep its heat for an extended time. It's one thing about Mars, it's smaller, so you have a larger surface to volume area, and it can lose its heat quite quickly. If you lose your heat, your core stops and your magnetic field dissipates. The mass of the Earth is also large enough to allow for tectonic plates, so those big plates that float around on the top of the Earth, and they crash into each other, and it's where the continents are. And the tectonic plates, their motion, and one going under another, subduction, this all helps regulate the climate on Earth through a very complex carbon dioxide cycle of volcanoes venting carbon dioxide, dissolving in rainwater, eroding rivers, going to the ocean, settling down, and then the carbon can be trapped or sequestered in the Earth's within the Earth and taken out of the atmosphere. So if you have that tectonic plate, you get to sequester a lot of the carbon dioxide. One thing Venus did not have, or does not have, are tectonic plates. So its atmosphere is 90%, I think, carbon dioxide. It's a runaway greenhouse effect on Venus. And a massive enough Earth, it allows it to hold on to an atmosphere. And an atmosphere will filter out ultraviolet light, which is very damaging to life. It'll stop a lot of the meteoroids and other types of radiation. Our Earth also has, oh, I should have done that, a stable axial tilt. Now this axial tilt, right, so 23.5 degrees that we are tilted on in relation to our orbital plane, allows seasons. And seasons help maintain a balanced ecological systems while still providing varied opportunities for evolution. The seasonal changes in precipitation and temperature affect soil moisture, evaporation rates, river flows, lake levels, snow cover, etc., and contribute again to the erosion and recycling of material. And the planet would also be colder if it did not have a significant tilt. So if it was straight up and down, the greatest intensity of radiation from the sun would always be on the equator and maybe a few degrees above and below that. And the warm weather could not move poleward as it does on our Earth. You would actually have a polar dominated weather systems. The colder air from the north and south would seep down to the equator. The hotter air there would rise. So you would have a cooling of the atmosphere. We also have a large moon, and this helps to stabilize the tilt that we have. And the moon, of course, makes the tides on Earth, and the tides allow dynamic churning of the oceans on Earth to mix up the minerals, etc., that we have there. So I'm just going to show you now a few animals that either do exist or have existed on Earth's during Earth's lifetime. And it shows a wide variety of adaptations. So this is one of my favorites. He's called the Blob Fish. And so just this varying ones, this one is a prehistoric one. Here we have a bug that's alive now. Another fossilized prehistoric animal, and another one, a swimmer. Trilobites, of course, they were really, came into their own about 500 million years ago. Another prehistoric one, a Yeti crab. I think that's pretty interesting. And a little AIAO, and everybody's favorite, the tardy bear, the tardigrade or the water bear. This little guy is really amazing in his ability to live just about everywhere, even in space. He can be frozen solid, exist for quite a while, and then rewarmed, and he comes to life. So we're showing a wide variety of adaptations to all those different conditions that we have on Earth. So, you know, with our imaginations being, you know, looking at all these things, we can, pretty much anything we can imagine to be look like life on in the universe is probably out there. So what do we need for life? There are basically three things. You need ingredients, so minerals and waters and amino acids, especially the carbon, oxygen, nitrogen, hydrogen, phosphorus, and sulfur. Those are very important compounds. We need a medium to bring them all together and allow mixing. So if it's a solid thing like an asteroid, it doesn't matter really how many molecules you have on there, there's no mixing allowed, so the evolution of molecules can't take place. In atmospheres like Jupiter or Saturn, there's too much motion, so any molecules that might come together and stick together are going to be the turbulent flow up there will mean they don't stick together for long, and so larger and larger molecules are not allowed or not easily made. And you also need an energy source, and ideally it's solar, but we know it's not restricted to solar energy. So thinking of that, here are a bunch of molecules that have actually been found in interstellar or circumstellar places. So stuff between stars and stuff around stars where planets are evolving. And almost every one you can see has carbon and hydrogen in it. There's sulfur, there's some with oxygen, nitrogen, but a common thing to most of them is carbon and hydrogen, especially in these very, very complex molecules. And why do we use carbon? Go back. Or why does life use carbon? Well, carbon is special because it is very flexible. It can combine, it has 4 valent electrons that it can combine with other elements, and it can do it in lots of different ways. Carbon can make straight chains, can make rings, very complex configuration, and it can even make, if you see over here, this is a 60 carbon molecule called a buckyball, and they have been actually found in space. The medium most likely used is water. And water is very special because it is a slightly polar molecule. It is slightly positive at one end and slightly negative at the other. It's called a universal solvent, although it can't dissolve everything, because if it could, we wouldn't have any containers available that we could use for it. But it is, there are hydrophilic, so water-loving molecules like salts and sugars and some of the gases. And there are also hydrophobic molecules like fats and oils. And those are a good thing, because the fats and the oils would be able to be used in membranes, so we can separate cells from the liquid that they're in, the oceans and whatever, the water that they're in. So the fats and oils allow membranes to form around molecules. Life also needs to take in ingredients to make energy and food, flush out waste products, and again, because of water's knack for being able to dissolve all kinds of substances, it does make an ideal liquid for both the tasks. Water is also special because it has a wide temperature range where it is liquid. The other liquids that are considered possible for life are ammonia, methane, and ethane. But we can see they operate at very, very low temperatures. And in chemistry, the lower the temperature, the slower the chemical reaction. And these have, well, ethane's a little bit large, but most of them have a very narrow temperature range. So of the liquids easily made in the universe, water is the best and certainly would be used by most things, as it's on just everywhere in the universe. And one of the unique things about water is that when it is frozen, it floats. All these other liquids, when they freeze, they sink to the bottom. So if you have an ocean where you've got hydrothermal vents at the bottom and life being formed and life evolving down there, the Earth has gone through several snowball Earth periods where the entire outside freezes. Now, if your ocean freezes, it would freezes and all that ice on the top sinks, you're going to kill all the life down there. Or if the ocean freezes and the ice floats, you're kind of protecting that liquid and the life that lives there. And in fact, even though we have had some major icing events on Earth, once life got started, it was never stopped. Certainly not by this. So I've just made a quick conclusion that life in the universe most likely will be carbon-based. Carbon is the fourth most abundant element in the universe. Of course, hydrogen and helium account for 98% of the elements in the universe. Oxygen is 1%, and carbon is 0.5%. Life will most likely be on a planet that has liquid water. So again, we're looking at that habitable zone. Is similar in size to the Earth, and that's probably about half an Earth to 1.5 Earth masses. If you have a planet with a low mass, you get a quicker loss of heat, which leads to the loss of the magnetosphere, the magnetic field around, and that's exactly what happened to Mars. And when your magnetosphere disappears, any atmosphere you have is more susceptible to being stripped by the solar wind from the star. A very high mass Earth or planet would have a very dense atmosphere would have lots of captured hydrogen and helium, just like Jupiter and Saturn. And this would delay any other type of atmosphere formation in having the atmosphere change to a more sustainable one for life. And a thick atmosphere would also prevent photosynthesis. Now, we know that chemical production of energy can happen at these hydrothermal vents. So there still could be life down at the bottom of the oceans, but life would not be able to evolve to have photosynthesis and make use of the sun. The planet would also orbit a star similar to our sun. Stellar stars are divided into these main categories. These are very hot, very massive stars, and these are very small stars. These are the red dwarf stars. Our sun is a G star. So if you went a little warmer than our sun to an F star, that'd be a star a little bit bigger, a little hotter, that would be okay. Or if you went a little cooler to a K star, a little bit smaller star, a little bit cooler, that would be okay also. But outside that range, you have these very hot stars not living long enough and producing massive amounts of ultraviolet light. And then the red dwarfs, which we've already talked about, the small stars where you would have tidally locked planets. Again, it would have a fairly circular orbit. That means that the planet is always in the habitable zone. If you have a very elliptical orbit, the planet might go through the habitable zone, rarely, spending most of its time either too close to the sun or too far away from the sun. So the ability for evolution to happen would be narrowed. And you could also find life, as we've talked before, on a moon that would have similar suitable conditions like we're finding on Europa and Enceladus, where you actually have also liquid water. And I'm sorry, but that's all I could put together for this week. Are there any other questions? Oh, are there any questions at all?
Yeah, no, that's super interesting. And when you think about, I mean, maybe we can just kind of go around and see what people's initial reaction or kind of takeaway is. We'll just go down the list here. Wyatt, what was something that you found pretty interesting, Mr. Anderson?
I found it pretty interesting about what animals can live in what environments, and I thought that was really cool. And I had no idea there's a place like that. Is it Ethiopia? Is that what you said?
Yeah, Ethiopia.
That's pretty cool. I thought that was cool.
Yeah, the only place where we have found no life.
Will?
Yeah, that was a lot of information, but really cool. There's a lot of things I was like, oh, it's kind of neat. You know, it is weird that, like, yeah, a planet has to orbit a certain way to be able to sustain life, because if it goes too far away, it won't sustain life, or it goes too close, it won't be able to sustain life.
Yeah, exactly, yeah.
Newman? Thanks, Will.
Yeah, I feel like for some people this would be a really good way to have an existential crisis about how small of a chance there was for us to exist and us to currently exist right now. But it's just really interesting with all that and all the tiny little puzzle pieces and like just something happening that was like 1 in a million kind of chances. So when you think about it, we've already won the lottery, all of us. But yeah, it's really interesting.
Well, putting all these limitations on life, you might initially think that that means it's nowhere. But if we look at all the exoplanets that we're finding, and we're certainly finding Earth-sized exoplanets now, and every star has, you know, an average of probably at least 2 planets. We've just found a system that has 8 planets, just like ours, except they're all much closer to the star. Anyway, my point being, there are lots and lots of opportunities for life to get started. The evolution toward intelligent life would take certainly different paths, and they say for the most history of the Earth, there has been single cell life, and that has been it. So finding another planet that has intelligent life might be much more narrower, but certainly finding planets with life, I think within the next 10 years, we'll be finding them all over the place.
Wyatt Clapham.
I think it was very interesting when Colleen mentioned the tardigrades.
Yes.
I really liked that part.
Yeah, they're
extremely fascinating.
They are. They can travel in space. So did they originate here, or did they originate elsewhere? Probably originated here, and just one of its evolutionary steps also included the ability to be in a vacuum and not die. Might not have been a favorable gene trait, but it certainly didn't hurt the little bug.
Yeah.
Was it last year or the year before we actually we had isolated some tardigrades? I think it was Zach. Was that you and Ethan? And we were able to look at them under the microscope.
Oh, cool.
Two little guys in there. We got it off a lichen up in the mountains.
Oh, neat. Yeah, they are everywhere.
Yeah, super cool. Where are we at here? Sharon, what'd you think? you still there?
Yeah, I am here. I'm sorry, I've been on a few different calls, but I was definitely fascinated, and I loved all the alien life forms. And as always, I'm just blown away by how incredibly smart you are, Colleen.
No. I do like
It's
astrobiology,
amazing. It's
though.
so cool.
Caleb.
You are definitely an amazing resource to have, and I don't really know if our students realize how incredible it is to glean your knowledge. So thank you so much.
You're very
My
welcome.
head's just like.
Caleb.
The presentation was really interesting. I didn't know half of it, or like most of it, but
Good.
it was really good and I really liked it. So yeah.
Zach.
Yeah, I thought it was pretty interesting. What really got my attention though was the different animals that like lived on Earth before us and even with us. Because like I've heard of like blue the blue dragon that's
Yeah.
live in I think Antarctica. I think.
Yeah. That's,
So I heard of him. I did a little presentation about him in science.
so neat. Yeah. Beautiful
Yeah,
little animal.
yeah, and also that was interesting to me is that of how the current projects that are happening right now to like clean out all the debris in
Yeah.
space. So that was pretty interesting.
And again, SpaceX is trying to mitigate that by having their rockets returned to Earth and reused.
Right.
There are other ways to do it. Just one thing about the variety of life that we can find on Earth, and how life just fills every little ecological niche. People often are sidelined by thinking that how can evolution have caused all this? How did those plants and animals know to evolve in a certain way? The one interesting thing that I found out when I took an astrobiology course is every cell of your body is producing over 2,000 proteins every second. Some of them will be used and most of them will not. But if any one of those proteins happens to do something a little bit better, it will be incorporated into the cell. So that gives an absolute continual feedback, sort of, having all these tools available, and if any one of them gives you an advantage, that you can use it. So 2,000 proteins a second. That really opens up the ability to evolve to any circumstances.
And I guess, you know, in evolution, it's not like it's a predestination, like it's not like it's already predetermined. It's like things are changing, and it's the climatic and environmental pressures at the time that are dictating what's
Yeah.
able to survive, and not just survive, because it has to be able to reproduce.
Yeah, it has to be able to survive better. Yes.
Yeah, no, my thoughts watching the presentation was much kind of like Newman's, and just all of the different things that had to come into place for life as we know it to be able to evolve here, right? From the moon to the orbit to, and it seems like a big problem is UV and cosmic waves and just things that denature our cells. Right.
That's
and
right.
our cells can't continue on with their regular cell cycle, right? And when and so what would happen is people get cancer, right? Your denature cells and cells would grow out of control. So having a magnetosphere and having all those things around us, I mean, yeah, just so many things had to fall into place.
And in a universe as large as ours, it has probably happened in a lot more places also.
Yeah, for sure. Yeah.
2 trillion galaxies with 200 billion stars, each star an average of 2 or 3 planets. Certainly opportunity for life everywhere.
Yeah, cool.